Hey everybody, let's take a look at some relative motion involving an object that is undergoing rotation and translation. So we're going to do a ring or a disc. We got both of them here. And what I want to take a look at is when this object moves along this tabletop, how far or how fast, however you want to look at that, does a point on the top of this ring travel? So what we're going to do is we're going to take this meter stick and we're going to put it on top of the ring. Okay, and I want you to think about the fact that the meter stick's in contact with the top of the ring, this right-hand side. Now the right-hand side of the meter stick won't be in contact with it for the whole time, but we want to figure out how far is the end of this meter stick moving as it translates with the ring. Okay, so I roll the ring and keep the meter stick stationary on top of the ring. And as it moves across the table, okay, and you can see there's a meter down here, and I haven't quite gone a full meter on this, but as it moves across the table, the end of the meter stick is way out there. Okay, so if I measured, this is at about 1.85, not 1.85, but 0.85 meters is where this is at right here. And if I looked at where this end of the bottom end of the meter of the ring is, it's at about 0.85 from across here. Of course, I'm not all the way to the left, but that's because when I started this, the bottom of the ring was down here, right? And when I end it, the bottom of the ring is about here. So 0.85 meters. So the end of the meter stick has traveled 0.85 meters as the wheel has rolled 0.85 meters. Now, it's possible maybe that that's a matter of the size, the radius of the wheel. So let's do this one as well. This one's actually a little bit closer. It's about 4 centimeters from the edge of the table when it's right up against it. And so as I move this down, and I'm rolling down here, I get to here, and I'm about 8 centimeters from the end, so 4 centimeters from this end, right? I can measure that out as I go down to here, and that's about maybe even 5 centimeters. So let's say 5 centimeters, 5 centimeters. So I've traveled 90 centimeters, and let's do it again, but you'll see that the end of the meter stick, as I've gone down that distance, okay, there's too much sliding on that one, let's try that again. Okay, so the end of the meter stick, whoops, there we go, is at about 0.9 meters or 90 centimeters. So the wheels move 90 centimeters, the ruler has moved 90 centimeters, so the end of the ruler is at 1.8 meters from this left side where it started. And so the top of the wheel is moving at twice the speed, because it moved at twice the distance in the same amount of time as the middle of the wheel. And what we want to do is we want to examine why is that happening? What are the equations that govern that motion? And that's what we're going to do here in just a little minute. All right, let's take a look at that rolling ring that we looked at a little bit earlier. And so here's the ring, and I put a little piece of white paper on there, and this thing is going to roll, okay? And I want to think about what's happening with this piece of white paper as it reaches this bottom point. And what you'll notice is that the white paper is going down, and then the white paper is going up. And so the velocity of the white paper is down, and then it's up, and so it's gone from negative to positive. So somewhere in there, according to the intermediate value theorem in calculus, it must have passed through a velocity of 0, at least in the up and down. So what we're going to say is that the velocity of this piece of paper, as it's at the bottom, that velocity right there is 0. It's not moving with respect to the board here, okay, or the ground, if you will. That piece of paper is not moving in that instant. Now, it will be very quickly, but in this instant in time, the velocity of that piece of paper is 0. Okay, we want to take advantage of that. So the velocity on the wheel is 0 when it's in contact with the stationary surface. Now we got to be careful if that surface is not stationary. But we're not going to worry about that at this point in time. We'll talk about that later on, okay? All right, so the velocity is equal to 0 there at the base. All right, so let me just make that statement then. The velocity of O is equal to 0. O is the origin of my system. All right, so I've got a wheel. It's got a radius of R. The center point is A. The upper point, remember that's where the ruler was. The upper point is B. And what I'm interested in is the velocity of B. But let's take this one step at a time. First off, what's the velocity of A? So I've got a wheel that's undergoing rotation. It's going to have some constant velocity, angular velocity of omega. It doesn't have to be constant, but let's keep life simple. It's going to have some angular velocity omega. And in this case, it's clockwise, so my thumb points into the board. So omega vector is equal to omega k hat, and that's going to be negative because it's clockwise. My thumb is pointing into the board. And then A has a position with respect to O. The position of A with respect to O is equal to R, the radius of the wheel, times j hat. And so velocity, recall from a previous video, the velocity of A with respect to O is equal to omega crossed with R of A with respect to O. And so what is that? That's going to be minus omega k hat crossed with R j hat. So I get minus omega R, and then k cross j, if I go back to my unit, my cross product unit circle, k cross j is I, but I'm going in the wrong direction. Okay, the arrows, remember, point counterclockwise, I, j, k. So k cross j is negative I. So there's a negative I hat here. And so my velocity is actually negative, and negative is positive. It's omega r I hat. So the velocity of A with respect to O is omega r I hat, that vector value. A lot of books will just call this the velocity of A. And if I don't have a subscript, it's understood that that's the velocity with respect to some fixed origin, which in this case, again, is the ground, or the contact with the ground. All right, so what's the velocity of B then with respect to O? Well, in a similar fashion, I can say the velocity of B with respect to the origin is equal to the velocity of B with respect to A plus the velocity of A with respect to the origin. Remember that we looked at the subscripts in relative motion, and I've got B over A over O, the A's go away, and I get B with respect to the origin, so that's working out just the way I want. All right, so the velocity of B with respect to A, well, A is a wheel turning, right? This is a wheel undergoing rotation, so it's omega, I'm going to call it omega AB vector crossed with the position of B with respect to A. That's the velocity of B with respect to A. Omega AB and omega are the exact same thing in this example, but in general it's the however this AB is spinning, right? Then plus the velocity of A with respect to the origin. But this is just equal to minus omega k hat times, or cross with, R times j hat, right? Because the position of B with respect to A is the radius of the wheel, and it's upward in the j direction. And again, k cross j is negative I, so this becomes minus, and minus becomes plus. So this is omega r I hat, but the velocity of A with respect to O is also omega r I hat. And so this is equal to 2 omega r I hat, which is saying what? The velocity of B is twice the velocity of A. And that's what we saw when we rolled the ring. The ruler went twice the distance that the ring went. The ruler went twice the distance the ring went. That's because, in the same time period, and that's because it has twice the velocity. The ring goes omega r times time. The top of the ring goes 2 omega r times time. And so the idea here, again, is relative motion. Right? So this is the equation we want to look at, and the velocity of B with respect to A is right there. Okay? And that's just, let me get rid of that for a second. That's just the spinning rate, the rate of rotation that's taking place, crossed with vector cross product, the position of B with respect to A. And that's going to be our relative motion sequence. All right, and we're going to look at that at length in the next couple of videos.